Hi everybody and welcome to the last chapter in our course on integration. So this is going to be quite a long chapter spread out over many different sets of videos, about 4 of them, but it is the last chapter. So in today's set of videos we will cover the basic definitions, the indefinite and definite integral, the relation between the definite integral and area. So this is a very important property and it explains why we care about the integral in the first place. And then we'll finish off with some properties of integrals and a couple of worked out examples. So let's dive right in and define what we mean by an integral. So for the purpose of this course, we will see integrals as antiderivatives. And what does that mean? Well, the anti basically here means that it is the opposite of a derivative. So for example, we know that the derivative of x to the power 3 divided by 3, that is 3x squared divided by 3, or in other words, that is just x squared. So from that, what we can say is that the integral of x squared dx is equal to x to the power 3 divided by 3. So a couple of things to note here. So this long s, this is the integral sign. And this is sort of a stylized S. And you can think of this as a variant of the sigma sign that you know from summing things. The relation between summing things and taking integrals is a very fundamental one and will be explained in the second part of Mathematics 1. And then the other new element here is dx. So this we call the differential of x. So it looks a bit like the d in a derivative, and that is also not a coincidence. We'll come back to that later. So now, one other thing to note is that it is true that the derivative of x cubed divided by 3 is equal to x squared. But what we can also do is we can add any arbitrary constant to x cubed over 3. And ddx of a constant is just 0. So adding a constant to x cubed over 3 does not change the fact that the derivative is x squared. So for the integral, what that means is that the integral of x squared dx is not just x to the power 3 divided by 3, but it's that function plus an arbitrary constant. So this c here is an arbitrary constant. And in this way we obtain what we call the indefinite integral. And so if you know how to compute derivatives, you can compute integrals. And that means that we get a lot of integrals for free. So we know that we can derive that the integral of x to the power n is equal to x to the power n plus 1 divided by n plus 1 plus, again, an arbitrary constant. And this holds for n different from minus 1. And why is that true? Well, because if we take the derivative, then we know the derivative of x to some power, that's the power times x, and then you reduce the power by 1, so it's xn, and we still have an x, an n plus 1 in the denominator, so this is just xn. So at this point in time, if we want to compute an integral, we sort of have to guess what function the derivative is going to give us. What we will see in the remainder of the course is many different ways of computing integrals. So a couple more that we already know. We know that the integral of sine x dx is equal to minus cosine x plus a constant. Again, because if we take the derivative of cosine, that's minus the sine, so the sines cancel out. And then integral of cosine is sine x plus c. And we can continue with some more trigonometric functions. The integral of the secant function is the tan function plus a constant, always plus a constant. The integral of cosecant squared x is the negative of the cotangent. And then a few that are more complex looking, so secant of x times tan x dx is secant x plus c, and integral of cosecant x cotangent x dx is negative cosec x plus a constant. So all of this we know from the rules of the derivative, because we know that, for instance, d dx of minus cosine x is sine x, d dx of sine x is cosine x, and so on. All of those rules that we derived previously for the derivative now give us examples of integrals. So especially the first few are really important to keep in mind, just like the derivative of sine and cosine were important. Now let's look at some inverse trigonometric functions. So here we knew, for example, that d dx of sine inverse of x is equal to 1 over the square root of 1 minus x squared. So that tells us that the integral of 1 minus x squared is sine inverse x plus a constant. And then by the same token, by looking at the derivative, we also have that integral of 1 plus x squared is the inverse tangent function plus c. And these are useful ones to keep in mind as well, because you will often encounter an integral of a rational function or square root of a rational function, and then you will see some inverse trigonometric functions propping up. And then a few more, the exponential and the logarithmic functions. So we know that the derivative of e to the power x is e to the power x. So that tells us that the integral of e to the power x dx is also e to the power x plus a constant. Likewise, we know that d dx of ln x is 1 over x, and that tells us that the integral of dx over x which is the integral of 1 over x dx. That is the ln, the logarithm of the absolute value of x. So here it's just a little bit different because you have to take into account that logarithm isn't defined for negative values. So here you have to take the absolute value. And so as a quick side note, we already know that the integral of x to the power n is x to the power n plus 1 divided by n plus 1 for n different from minus 1. That's what I already explained on the previous slide. And now the rule about the logarithm gives us the rule basically for what happens if n is equal to minus 1, because this tells us that the integral of x to the minus 1, or 1 over x, that's the logarithm of the absolute value of x. So the integrands look very similar, but the outcome is very different when n is minus 1. And then if you know these two, you can also derive that the integral of a to the power x dx is equal to a to the power x divided by the logarithm of a plus a constant, and that again follows from the derivative rule. So that gives us the indefinite integral, and there's a slightly related concept known as the definite integral. So this is basically an integral with boundaries, for lack of a better word. So what do we mean by that? It is a quantity integral of a function f of x dx, but now you have boundaries a and b in the integral sign here. And the way that we read this is as the integral of f of x with respect to x over the interval a, b. And the role of this interval will become clear when we talk about the relation with areas. And so to unpack this notation just a little bit more, so this a we will call the lower limit of integration, and then likewise the b is the upper limit of integration. And then the f of x, just like for the indefinite integral, this is known as the integrand, and the d of x is the differential. And now you wonder, well, okay, how do I compute this thing? Well, there is a rule for that. So you have to initially at least work in two steps. So the first thing that we will do is we'll write the indefinite integral as a function capital F of x. So what we will do is we'll take our indefinite integral and we'll call that capital F of x. And we know that our indefinite integral is only defined up to the addition of a constant. And here what you can do is you can choose this c, the constant, you can choose that arbitrarily. So for instance, but not limited to c equal to 0. And the reason why you can choose that arbitrarily is because having the antiderivative, now what we can do is for the definite integral, now we have that the integral from a to b of fx dx is the function capital F evaluated at b minus the function capital F evaluated at a. And we also write that as follows: f of x evaluated at b a. So vertical bar means evaluated at. And this last piece is notation, but it is very useful notation. So also here, the definition of the integral is you take the antiderivative, capital F, you evaluate it at the upper limit of integration, and you subtract the lower limit of integration. So let's look at an example. So first, let's compute the integral from 0 to pi over 2 of sine x dx. Well, first of all, we know that the indefinite integral is negative cosine x plus a constant. So for the definite integral, what we have to do is we take the antiderivative, negative cosine x. Here we set c equal to 0. We know we can choose any value of c, so 0 is a good one. And then we evaluate pi over 2 and at 0. And then this works out to, this is negative cosine pi over 2 plus cosine 0, so it's minus minus, gives us a plus. And this is of course 0 plus 1, so 1 for the integral. And then secondly, let's compute the integral minus 1 to 2 x squared plus 2x minus 1 dx. We don't have an antiderivative for the integrand here, so we have to guess a little bit. And in a minute we will see rules for dividing this integral up into smaller pieces that we can easily compute. But for the time being, I'm going to give you the antiderivative. So here, if you use x to the power 3 divided by 3 plus x squared minus x, then you can check for yourself that the derivative of this is x squared plus 2x minus 1. And now having that antiderivative, again we evaluate at 2 and minus 1 to get our answer. So we get 8 divided by 3 plus 4 minus 2. So this is f evaluated at 2, if this function here is f of x, and then we have to subtract from that minus 1 over 3 plus 1 minus minus 1, and that is f of minus 1. And now of course we can simplify that a little bit, and you should get 14 over 3 minus 5 over 3, so that is 9 over 3, or 3 in total. Now, a couple of useful properties to compute definite integrals. So first of all, if we take the integral from a to a, so the same value in the bounds, then we always get 0 no matter what the integrand is. And we can derive that by looking at the definition. So what is the value of this integral? It's the antiderivative evaluated at the upper bound a minus the antiderivative at the lower bound, which is also a, so that subtracts to 0. So whenever the bounds are equal, you always get 0. Secondly, if we take the integral from a to b of fx dx, by definition that's big F of b minus minus big F of a, and now we can write it as minus fa minus fb, so just taking out the sign. And then what we have inside the brackets, that's also an integral. That's the integral from b to a. So if you switch the upper and the lower bound, then you get the integral with a different sign. Third, a very useful property. If you take the integral from a to b of a constant times a function plus another constant times another function, then you can take out the constants and take the integral of each of the functions like this. So for example, so this is an example of rule number 3. What we had in the previous slide was the example x squared plus 2x minus 1 dx. So we could have written that as integral of x squared plus 2 times integral of x minus integral of 1, and then we can use our rules for the polynomial, so we know that integral of x to the power n is x to the n plus 1 divided by n plus 1 plus a constant. And so then we can work out the integral to say, well, integral of x cubed, x squared is x cubed divided by 3, evaluated at 2 minus 1, plus 2 times integral of x, that's x squared divided by 2, evaluated at 2 minus 1, and then minus, so what is the integral of 1? Well, it's the same rule, but with n set to 0, so the integral of 1, that's x, and here we also evaluate at 2 and minus 1. And then if you substitute the values, you can compute for yourself that you get the same answer, which was 3. So rule number 3 is also a very important one. And then number 4, if we take the integral from a to b of f of x dx plus the integral from b to c f of x dx, that is the same as the integral from a to c f of x dx. Here you have to be careful. You have to have the same integrand in order to conclude that the two integrals can be summed together. The same integrals, and also the upper bound here has to be equal to the upper bound here. And then last, a very fundamental property, and that is the fact that definite integrals can be used to compute areas. So in other words, definite integrals correspond to signed areas. And why that is so, you will see in the second half of this course after the vacation, but we can already give some intuition and talk a little bit about how that works. So if we have a function f of x, and I'm going to graph it here, which is entirely above the x-axis, So this graph is y equal to f of x. And if we take 2 points on the x-axis, a and b, then the shaded area is equal to the integral from a to b of fx dx. So this area right here, this shaded area, is the integral from from a to b of fx dx. And this is if f of x is bigger than or equal to 0, so if it's above the x-axis. So now what happens if f of x is less than 0, so if it's below the x-axis? So in this case we have a function that looks maybe a little bit like this. And we have 2 points A and B. Then we know that areas are always positive. They're always quantities that are positive. And then what we get is that the area is no longer just the integral, but now it is minus the integral. This area right here, for a function that's below the x-axis, is minus the integral. And then last, you wonder what happens if f of x changes sign. So let's say we have a function that crosses the x-axis a couple of times. And now let's say we have our a here and our b here. And we want to compute the area between the graph of the function and the x-axis. Then what we have to do is we have to calculate in multiple steps. So this area here, A1, for that we know that this is equal to the integral from a to where the function crosses the x-axis, so let's call that c. And then now here the function is negative, so if we call this second part here a2, and if we define it as the part that's below the graph, or between the graph and the x-axis, between c and d, then a2 is minus the integral c to d of f of x dx. And then last, the remaining part here, let's call that a3. So here the function is again above the x-axis, and therefore we know that a3 is integral of from d to b fx dx. So from that we get that the total area is integral ab fx dx minus integral cd fx dx plus integral db fx dx. So let's do a couple of examples. For the first example, For the first example, we will look at the area between the graph of sine x, the sine function, and the x-axis between 0 and 2 pi. So in order to do that, let's graph our function first. So this is the familiar site. We have one full oscillation of the sine curve. This is 0, pi, and 2 pi. And what we want to know is this shaded area. So for the area, we know that we have to look at where the function crosses the x-axis, which is at pi. And then we have to add the areas above the x-axis with a plus sign and the ones below with a minus sign. So in this case, this gives us integral 0 to pi sine x dx, and then minus integral pi 2 pi sine x dx. Integral of sine is negative cosine, evaluate at pi 0, minus, again, negative cosine, evaluate at 2 pi pi, so that's minus cosine pi plus cosine 0, and then minus cosine 2 pi plus cosine pi. And so now you can evaluate all of those values. So cosine of pi, that is minus 1, so we get plus 1. Cosine 0, that's also 1. And then minus, so cosine 2 pi, that's the same as cosine 0, so that's minus 1. And then cosine pi, again, that is minus 1. So we get 1 plus 1 plus 1 plus 1, which is equal to 4. Secondly, let's find the area below the graph of y equal to 3x minus x squared and above the x-axis. So here we're not given the explicit bounds for the integral, and we have to look at the graph to decide that. We can graph y is equal to 3x minus x squared, and we get a function like this, which passes through 0 and 3. And from the problem statement, now we have to find this area below the graph, but above the x-axis. And so here our area is equal to the integral 0 to 3 of 3x minus x squared dx. So let's calculate that, and we'll calculate it once very slowly. Integral 3 times the integral 0 to 3x dx minus integral 0 to 3x squared dx. So that is 3 times, now we choose a primitive or an antiderivative, x squared divided by 2. We evaluate 3, 0 minus x cubed divided by 3, that's a primitive or an antiderivative for x squared, and we evaluate that at 3, 0. And then if you substitute the values, we get 3 times 9 divided by 2 minus 0 divided by 2 minus 27 divided by 3 minus 0 divided by 3, and so we get 27 divided by 2, 27 divided by 3, and if we simplify that, we get 9 divided by 2 for the area.